Okay, so then let's get started. So from the last week, we started to discuss some kind of some techniques that can basically that are basically about some kind of inference-time guidance, which means that with some kind of the pre-trained diffusion or the flow of the models, how can you basically inject some kind of the usual guidance at the inference time, at the test time, in a way that the output becomes something that the user wants to see. So for that, while there are actually lots of the techniques for that, I mainly basically introduced like those three categories. And the first thing was basically about some kind of like manipulation of the score and the attention. And for that, actually, there are some kind of some engineering idea in terms of how we can basically manipulate some kind of some intermediate layers of the neural network, or how we can also manipulate the output of the neural network in terms of manipulating those things. So those are the cases that we can provide some kind of the direct and the strong guidance. Obviously, the problem is that there's no theoretical explanation for this, and also it can be only applicable to the very specific cases, especially for giving some spatial guidance for the images. It can be extended to the other data modalities as well, but this was kind of the case. So we started to discuss some kind of the slightly more kind of some different way, which is having some kind of the more theoretical explanation. And while we titled this as kind of the gradient ascent from the future world, actually the things that we discussed last time was basically about the inverse problems, right? So the inverse problem was defined in this way, basically given some kind of here, basically given the observation the y here, and some kind of a mapping function the a here, how can you generate the x that can satisfy this formulation in terms of that the x is aligned with the observation the y we have given this formulation, right? For those kind of the inverse of the problems. So the problem becomes like, how we can basically model this kind of the conditional score here. So this is basically what we want to compute, right? Given the condition the y, how we can compute the score for the xt. And then using the base rule, actually what we could see is that this marginal score is basically something that we are predicting using the neural net, right? And basically then we need to basically compute this kind of some sort of the offset into our score, which is now defined as kind of the other way of the conditional score, basically the y conditioned by the xt, right? So it became basically all the way to basically how are we gonna model basically this the conditional score without having any kind of the extra training of the diffusion the model. And for that, we briefly discussed some kind of the two ideas, especially for the case that when we assume that the inverse problem is basically defined as kind of the linear function like this, then we could basically derive that this conditional score term here could be basically computed in this way with some kind of some parameters, the R here, which was the case that we are computing the pseudo inverse of the A. And this could be further simplified when you have some kind of even more some kind of crude approximation in terms of like approximating this conditional distribution into this way, into this Gaussian distribution. Obviously, this would not be a simple Gaussian distribution, but the benefit of like having this kind of simple approximation is that now we can simply model the conditional score as kind of the gradient of the L2 loss this way. So this was kind of like one simple, very convenient way that we are modeling the conditional score, and in a way that we can inject some kind of the guidance at the test time. And basically also changing this score function using this term could be basically rewritten in our generation process in terms of basically not changing the score here, the noise here, but instead of basically modifying the final the sample at each step. So once we basically compute the next the sample, basically having the xt minus 1, by just like having this kind of like one step of the backpropagation, we could basically update the xt minus 1, which was basically equivalent with basically modifying the noise term there. So this was basically the basic idea. And also the good thing of like having this kind of the idea is that while it was kind of like derived from kind of some formulations, in terms of the implementation, this is like really simple. Just literally just adding like one line of the code into the generation the pipeline in terms of that we are basically injecting some kind of the guidance in terms of the final output should basically match the observation that we had. So I strongly recommend you to try this with your own diffusion model in terms of basically whatever kind of some kind of guidance you can do. And also the interesting aspect might be is that these are all the kind of the formulation based on the discrete, the time, the space, the formulations of diffusion models, right? Based on the DDPM deformulation. But we also discussed that actually there's the corresponding the continuous time deformulation as well, right? So this is exactly the same thing that we have seen in the SDE deformulation. So when the reverse SDE is basically defined in this way, I'm just like introducing some kind of the new term here, which is nothing but just like this entirely part. Then what we have seen in terms of basically reinterpreting the generation, the process of diffusion model is that actually the reverse process of diffusion model could be interpreted in this way in terms like just like solving this SDE with the time domain the discretization. And for that, basically, the whole process could be considered basically computing the score and this term and just like computing the xt minus the delta t in this way. So this is basically the same deformulation, but as basically seeing that as kind of the discrete, the time domain, the discretization of the SDE deformulation, right? Then basically what we can see is that here we are seeing basically how we can compute, the xt minus 1 by updating it with this kind of like extra, the additional term here, right? So the same thing also can be considered in the SDE formulation as well. So can you briefly write down in terms of like how is the reverse process of the DPS can be computed also using the reverse SDE as well. So basically the question is that when you think about this whole process in terms of basically adding this kind of some of the guidance into the sampling of the xt minus 1, how can you basically write the formulation for the same thing but based on the reverse SDE formulation? So for the reverse SDE, we are basically having those kind of the two steps, right? So this is kind of some simplified form of the generation here, right? Should be exactly the same thing. But if we basically inject this kind of the usual guidance into the continuous the SDE deformulation, what should it look like? Did you finish? So, I mean, this is basically nothing but exactly the same thing, right? Basically, once we basically compute, basically sample the xt minus the delta t here, we just need to do some kind of the update based on the gradient of the output loss here. So basically the same thing basically can be seen in the continuous time domain there as well, right? But here basically some bunch of the questions is that then can he apply the same idea into the ODE formulation as well? What do you think? What if we apply the same idea into the, not the SDE, but into the ODE formulation? Any thoughts? So actually, I recommend you to try this yourself. So that's why we are also having the kind of the team project, where you can play with those kind of things. I strongly recommend you to try this with both the SDE and the ODE formulation. There is no reason not to work. It should work. I mean, I guess with the ODE formulation, it's basically exactly the same. But basically, both for the SD and the ODE formulations, there might be some kind of some practical, some kind of the things, some issues. So basically, as you can see, this is like all, basically when you solve this like ODE and the SDD formulation, we might need to have some kind of the discretization of the time domain, right? So how many steps should we take in terms of like injecting this kind of noise? Would it be better to have some more number of time steps or the fewer number of time steps? Any thoughts? I mean, whatever we see, this kind of the SDE formulation or, sorry, the DDPM-based formulation, would it be better to have some kind of the number of the time steps or the fewer number of the time steps? No ideas? I mean, obviously, it'd be better to have some more number of the time steps because then we can inject this kind of some additional score, the more the number of times, right? So as we basically inject this kind of the score and the more, that will give some kind of the guidance towards to going to the final the output that we want to see, right? Then this question, basically the question becomes that, then there is basically some kind of the trade-off, right? Because like as we want to basically guide the trajectory of the generation, basically the path into the like going to the something that we want to see. It'd be basically better to have some kind of the number of the time steps, which means that the generation becomes like slower, right? So that's kind of some sort of the downside when you basically inject this kind of the guidance only at the test time things without having kind of any training. So if we want to take both the advantages in terms of the acceleration and also adding this kind of the guidance, that we might need to have some kind of the training the scheme as well, right? The training time to basically incorporate this kind of the additional the guidance. But the question also might be is that if we basically instead of like taking not the time steps, but fewer number of the time steps, but if we basically increase this kind of the weight for the additional discourse, then what would happen? So you can basically play with those kind of things, right? You can either basically increase the number of the time steps or decrease the number of the time steps, but just like increase this weight here, right? Basically, this basically involves some kind of the user parameter that we can choose. We can also think about like the meaning of like, increasing the weight here based on the formulations that we have. That will basically become some kind of even the worst, the approximation. So basically what we typically see when you basically increase the weight here is that we're gonna see some kind of the output that is basically aligned with some kind of given the condition, the observation here. But there is like more chance that the output will become unrealistic. I mean, even without seeing any kind of deformulation, basically what you can basically imagine is that as we have some kind of the additional discord here, the xt or the x minus t minus 1 there will go to some kind of the region that is basically becoming some kind of intermediate sample that the neural net haven't seen during the training. So the noise prediction will basically become the noisier, basically not the accurate noise, which means that the trajectory will go into some kind of the direction that the output becomes some kind of the unrealistic the data point, while the output would be more aligned with some kind of the given the usual the condition. So there might be some kind of the trade-off in terms of that how we can make some kind of the realistic the output while also satisfying the given the condition. So many of the failure the cases for those kind of the Inference-Time the guidance is that either the output does not really satisfy the condition that we are providing, or the output becomes like unrealistic while satisfying the condition that we are providing. So how we basically control those kind of the user parameters and also the number of the time steps in a way that satisfies basically the both things is kind of one of the critical part in the Inference-Time the guidance. Make sense? So this is really easy to try. While we are not having any kind of assignment for this, I strongly recommend you to just implement this with the code for the assignment 1, 2, or 3. Literally just like adding one line of the code into the generation, the pipeline. then you see that it plays some role in terms of giving some of the guidance, but it may not be that easy in terms of basically getting some realistic the output while still satisfying the condition. Any questions on this? Okay. So this is basically relatively well-known the techniques in terms of basically how we can add some kind of the inference time, some kind of the user guidance in the generation, the process of the diffusion and the flow models. And the topics that I'm going to mainly introduce for today are basically some more advanced, way more advanced techniques. And I don't think that we're gonna have time to basically discuss all the details for that. So I'm gonna focus more on basically giving some kind of the high level the ideas for those kind of the techniques. And also the context as well, basically why we discuss those kind of inference time, the scaling the idea. Because actually this is kind of the trend, not only for the diffusion and the flow models, but more the broader, the generative AI, the kind of the techniques. Especially for the LLM, we are already seeing some kind of the many techniques for the test time scaling. So I guess most of you would know this person. Do you know? Yes? No? You don't care? So this is the Ilya Tesutchkever, who is one of the co-founder of the OpenAI. And actually, if you are interested in like reading some of the papers about diffusion and the flow models, then you'll actually see that the co-founder of the OpenAI is actually one of the authors of the many important papers about diffusion and the flow models. This is quite interesting, right? So even if you see for example, the consistency of the models is also the paper having the Ilyas Skipper like as the one of the authors. So anyway, so he's many kind of like talking about like many things about the AGI, and one of the things that he was talking even like 1 year before was about the end of the era of the pre-training. So basically, the claim is that especially for the LLM, we already used all the data that we can use, everything that there exists in the internet. So since we already used like all the data that we used, even when we basically scale up whatever kind of things in the training time, whatever we scale up basically the size of the neural net and also the computation time in the training, the performance gain that we're gonna get by spending more compute in the training time would be quite limited, like this. So here the basic idea is that instead of like spending more compute in the training time, can we basically make some kind of the improvement in the performance by spending more compute in the test time as well? So that was kind of the big topic over the year, this year. And we already have seen lots of some kind of the good examples for that. This is already like it has been a while. I guess the O1 or the O3 have been introduced last year or something, right? Now even we are seeing the GPT-5 and the many recent models. And the kind of the shocking thing at the time, like when you see the O1 and especially the O3, was that there was some kind of the measure of like measuring the AGI kind of things, like how much the performance of the LLM is close to the human understanding. There was some kind of the benchmark for that. Before some kind of the previous models, the AGI score was like very low, like something like the 10% or the 20%. But when we start to see the O3 here, the AGI score exceeded the score of the 88, which is like huge jump from here, right? And this was basically the case that the OpenAI model started to spend some kind of the more time in the test time. So if you basically also click something like the thinking model in the GPT now, then it will basically take some more time to improve the answer. So that's the basic idea for the test time scaling. By spending the more compute in the test time, how we are going to basically improve the output of the generative AI, the techniques. So the OpenAI's the O1 and the O3 were basically very representative case in terms of how we can basically improve the performance of the degenerate models by spending more compute in the test time. And also we have some kind of another good example early this year. Do you know the DeepSeek? Does everyone know how DeepSeek works? No? Yes? Is it too simple question? I mean, DeepSeek was quite famous early this year, right? And the basic idea for the DeepSeek, I mean, the R1D model, basically here. I mean, obviously there are lots of things to discuss in terms of the DeepSeek models, but one of the main ideas for the DeepSeek, the R1D model, was basically having this kind of the thinking process. So it's basically not just like outputting some kind of the final kind of things, but let the LLM to produce some kind of some intermediate tokens in the thinking kind of the phase in terms of that mimicking some kind of like human thinking the process, making some kind of all the intermediate things. So this aha moment was quite famous in terms of that even the DeepSeek is fixing some of the errors in the previous thinking the process. So this was basically all the kind of the basic idea in terms of that how we can basically improve the outputs of these models by spending the compute not only in the training time, but also in the test time. So, and this like in the LLM side, many people are saying that this is kind of the future direction in terms of improving the quality of the outputs. So regarding the test time scaling, I'd like to recommend you to watch this video. It's an explanation from the Dan Roberts, who is the engineer in the OpenAI. So let me briefly play this one.
Well, let's do a thought experiment. Who does thought experiments? Albert Einstein. So let's do a thought experiment about Einstein. And let's imagine we go back to 1907 before he started working on general relativity, and we asked him the final exam question for general relativity. GPT 4.5 actually made this up, but I can verify that this is a valid sort of question that you might ask. And we're OpenAI, so we wouldn't ask Einstein. We'd ask Einstein v 1907-super-I. How to make sure we get maximum reasoning effort and maximum effort we would get. So Einstein, I guess he's a visual thinker. Something about elevators and free fall. This is when you study GR, you learn about this and you do some calculations. And there's the rubber sheet and the ball. And looks like he got distracted about quantum mechanics for a bit. Our models get distracted too. There we go. That looks like starting to get to a black hole. I also don't know how he thinks about himself in all these scenarios. And there we go. That's like the sort of black hole thing that I was going for with the wormhole. That's the right answer. Turns out GPT 4.5 couldn't get this right answer. We needed O3. O3 was able to get it. I think my role at OpenAI is mostly just checking physics calculations rather than AI research. But okay, the point is though, it gets the right answer, or Einstein would get the right answer, and it would take him about 8 years to solve the problem. Or what I'm saying is that, he would discover, and this is what happened, 8 years later, he discovered general relativity, he'd be able to answer this question. So our models think for a minute now, and they can reproduce textbook calculations and perturbations thereof, but we want them to make major contributions to the state of human knowledge and science. So coming back to this plot, how do we get there? Well, now let's focus on the left plot. The performance of the model improves the more we train it, and the sort of training we do is RL, or reinforcement learning. And so the main thing that I want to communicate in this talk is that we want to scale that up. A year ago, we put out GPT-4o. There was compute used, and it was all pre-trained compute. And as you can imagine, then we started doing this thing that led to test time compute. So we added some reinforcement learning compute, RL compute for O1. I should say this is all a cartoon, but directionally it's correct. O3 maybe had a little bit more RL compute. At some point in the future, maybe we'll have a lot of RL compute, and then at some far point in the future, maybe we'll have just be totally dominated and crushed by RL compute. And this is I think is kind of a contrarian point of view. This is where we're going. And we mean it to emphasize sort of the contrarian nature of this. This is some of you who followed AI research. This is a slide that Jan LeCun made some number of years ago, I guess 2019, based on the copyright that I borrowed. I borrowed this from obviously the this is a complicated slide that's maybe hard to follow. Luckily, we have models that can summarize things for us. The point is that pre-training is like this big cake, and reinforcement learning is supposed to be like this little cherry on top. And you know, that's basically what this plot was. The color scheme actually was accidental, but I think it actually works quite well.
So yeah, here the basic idea is that, basically this guy wants to explain like how the GPT can solve the problem in minutes, the problem that the Einstein was solving for the 8 years. So this is basically all based on some kind of the RL, based on kind of the the test time scaling in terms of having some kind of the more compute in the test time. So as also Dan briefly explained here, this kind of test time scaling, the idea is based on some reinforcement learning. So we're going to briefly talk about this without getting into any details for that. But as you can see, if we see some kind of the more recent models, even when you try the GPT the 5 for now, there will be some kind of the more thinking the phase, right? The thinking the model. If you click that, it will take some more time to provide the kind of the outputs. This is basically all involving some kind of the test time scaling in terms of like improving the outputs in the test time based on the more compute at the test time. So the topic that I'm going to briefly talk about today is that how we can also apply the idea, not for the auto-reasoning models, typically used for the LLM, but also for the diffusion and the flow models that we are discussing here. And if you are also more interested in the test time scaling the idea, there's some kind of some sort of the survey paper, which is talking about lots of the techniques for that. So check this out. So there are also lots of kind of the things you can try. So one kind of the side note is that, so what I basically also heard is that if you do some kind of if you see some kind of research groups working on the LLM side, especially for these days, they are not really focusing on just developing some single technique or just like making some kind of the papers here. They focus more on basically how to start up in terms of like making some kind of the new model that can outperform many existing models. But I'm not sure how this would be kind of the promising the directions. But the thing is that after we start to see some kind of the technique for the test time scaling, this is basically not about basically how we're gonna use the tones of the GPUs and handle like lots of the data to make some kind of the big the LLM or some big generative model. It's more about basically having some kind of some smart techniques that can be also working with some way fewer number of GPUs as well, compared to some kind of train the time they compute, right? So basically, here the hope is that we use even with some kind of the much smaller the amount of the computing resource, even at the test time, by applying those kind of the techniques, we can make some kind of the much further the improvement in the test time. So this basically motivates kind of like many people to think about making some kind of developing those kind of techniques, and also thinking about starting up in terms of basically beating the performance of the many existing models. So this is kind of, I think this is quite interesting the direction in terms of like how we can, what basically we can do, even with some kind of the much smaller the amount of the computing the resource, not with some kind of the training from scratch like those kind of the models, but with some kind of some test time kind of things. So this is kind of the direction. And while there are also, as you can see, there are lots of some kind of the techniques for the test time scaling. But the very basic idea for many of things for the test time the scaling is that we are basically having the proposer and the verifier. So this sounds like we are going back to the GAN framework, right? So actually the proposer basically means the pre-trained the generative model, and the verifier is kind of another model. It can be a neural network, some kind of some kind of the code, whatever kind of things, in terms of like just really verifying whether the output from the proposer is kind of the good or the bad. Then based on this kind of the verifier, so we can basically guide the proposer, or we can consider basically selecting some of the good outputs after making the proposal to basically propose like multiple the outputs. So that's kind of the high level the idea in terms of the test time scaling. So we're gonna get into slightly more details for that. And at the very beginning, what I'm going to introduce here is that how we can also interpret the idea that we have seen for the DPS case, solving the inverse problem in the context of that we are having the reward function. So basically, we can interpret this kind of the concept of having the proposer and the verifier as basically having some kind of the pre-trained the generic model. So in our case, that would be diffusion model, and also having some kind of the reward function. So this reward function is basically giving some kind of the guidance about some kind of the usual the preference. So when you have some kind of some final the output, the realistic the data point, if this like function the output is basically high, that means that it's like more aligned into the usual the preference. If the reward function is basically low, which means that the output is not really aligned with the usual the preference. So we are basically assuming kind of the case that we have this kind of some reward function that's basically giving some kind of the notion of the usual the preference as kind of some continuous and the differentiable the function. And what would be such kind of the case that we can assume some kind of the reward function? You can also think about many examples for that, right? So basically, for any case, when you have any sort of some differentiable, some discriminative the model, giving some kind of a score for the output, we can consider this is basically define some kind of the reward function here, right? And also what you can see is that the inverse problem, the cases that we have seen last time, is kind of some special case of the having those kind of like reward function, because we can always basically define our the reward function like this, right? So the minus of the L2 loss, basically as the L2 loss is basically small, it's increasing the reward function, right? When the L2 loss is high, which means it's like decreasing the reward function. So all the cases like the inverse the problem can be considered as kind of some special case, or like the cases like making some sort of the reward function. So this is really kind of the general framework that can be applied to the many applications, also to the many modalities as well. For not only for the images and the videos that we have seen multiple times, but also for the many other the cases, even that I don't know well. But for example, for those kind of the motion generation, what we can do is that we can guide this kind of the motion in a way that it should basically avoid those kind of collision to some kind of the object in the scene. So if we somehow define some reward function that is basically avoiding those kind of collision to the given some kind of the object, that can be used to this kind of some trajectory, like basically making the motion avoiding those kind of the collision to the kind of given things. And also for the many other some kind of the science problems that I'm not the expert for that. But for example, like for some kind of the molecular generation for many kind of things, we might want to make some kind of some molecule, some sort of the graph structure while satisfying some kind of condition. I don't know, I heard that there are some kind of questions like, we have some kind of the existing some kind of the molecular structure, and we want to make another the molecular structure, which can have some kind of the docking point with some kind of existing the molecule. So those will be some kind of the condition that we want to satisfy, right? For those kind of the cases, if we can define some kind of reward function, then we can also consider those as some the cases that we can apply the same technique. So there are actually lots of some of those kind of the applications. If you are also working on some specific applications with the diffusion and the flow models, then you can also consider finding such kind of the problems that you can easily define some kind of the reward function. So here the basic thing is that given this kind of the reward function, how we can provide some kind of the guidance in the generation the process. Actually, what I'm going to show is that the things that I'm going to explain here from the next slide is eventually will be exactly the same with the DPST formulation. So this is basically all about how we can basically interpret the same thing from the different perspective again. Okay. So I'm not gonna get into any the details for the kind of the RLD formulation, but this is actually based on some kind of the RL kind of literature. But without with any kind of some background for that, basically what we can see is that actually now we want to sample some kind of the final data point, not from the original data distribution, the P0, but let's say like we are defining some kind of the new data distribution in this way as some kind of the output of some kind of the maximization the problem. So this is basically some kind of the redefined the data distribution, and we want to sample from here. And how we define this is that basically this is defined as kind of solution of like this maximization the problem. So basically what we can see is that we want to define some kind of the new distribution, the P0 this star here, in a way that that becomes close to the original the distribution, while also basically maximizing the reward, the expected value of the reward. So when you basically sample from the new distribution, the rewards for those kind of samples should be maximized, right? So this is already showing some kind of the trade-off between how much the new distribution would be close to the original distribution, and also how much the samples from the new distribution will be maximizing the reward. So as I also mentioned from the DPS case, as we just try to maximize reward more and more and more, it might be the case that we are deviating more from the given the original distribution, right? But if we just simply sample from the given the distribution, then we might also have some of the cases that the samples are basically not having the high reward. So given this kind of the trade-off, we are finding some kind of the new the data distribution here in terms like finding some kind of a sweet spot with some kind of the weight here. So it's basically matter of like how much we are going to maximize the reward with the samples from the new data the distribution, while basically not being deviated too much from the given the original data distribution. Just like we are just defining the distribution in this way. So the thing is that now we want to sample the final data point, not from the here, but from the here, from the P0, the star. And if we simplify this, while skipping some details here, actually this formulation of the P0 the star can be rewritten in this way with some kind of the complex formulation, the Z0 here. Actually, it can be simplified in this way, having some kind of reward function and also the weight here. And actually, if you are familiar with some kind of the reinforcement learning, anyone who took the RL course before? No? Oh, okay. So yeah, so that's why I just said that. I'm gonna not getting into any kind of details for the reinforcement learning, but if you take the RL course for now, actually you're gonna see that many techniques, especially many recent techniques, are based on exactly the same formulation, but for the training, not for those kind of test time kind of things. So this is basically exactly the same thing that we are seeing some kind of the literature of the reinforcement learning. So, but the thing is that we are basically using some kind of the diffusion model, which means that we're going to have some kind of the intermediate the data points in the denoising step, right? So then what we also need to do is that we also need to know the distribution for the not for the final the output, but also for the intermediate data point as well. As I said, like for the diffusion and the flow model, especially the diffusion model, everything is about computing the score function, right? It's all about the score, which means that we first need to know the probability distribution for all the intermediate data points, and the purpose of like having this would be obviously is to compute the score function, right? And also while skipping all the details here, also what we can see is that the probability distribution for the intermediate data point xt is also defined in this way. So you can see that this looks quite similar with the distribution for the final the output here. So here we had that the reward function for the x0, the clean data point. We are simply replacing this as kind of the value function here. So this v function here that satisfies like this is called the optimal the value function. And so I'm going to skip so many details here. So the problem is that while it's relatively like easier to basically derive this form, basically except for like this z0, actually having this is kind of really kind of the something that we can compute, right? The problem is that for the distribution for the intermediate data points, there is no basically analytic form for those kind of the v function here. So there's no way to basically we can precisely compute this kind of those like the v function in here, which means that we also need to have some kind of the approximation there again. So if we follow like what we have done for the DPST case, we are also going to have some kind of some sort of the crude approximation in terms like approximating this value function using the Tweedie's formula in the revert. And you can see that actually this really basically follows like how we defined the new distribution here. For the new distribution for the final output here, it was basically revert for the final output the x0. And we are mimicking this in terms of then now we are computing the revert for the expected the output from the xt. So that can be kind of can be considered some kind of good approximation for the optimal value function. And you can see that this is quite similar like what we have done for the DPS case, right? We also need to basically approximate the score function of the xt with the score function with the x0, right? We're using the Tweedies. So doing the kind of the same thing in the RL-based formulation. And the good thing that we are approximating the optimal value function into this form is that now we can compute the score function, right? So let's say, like this is like all about like computing score. The computing score is basically made of like computing the gradient of the log of the probability. And now we know the distribution here. And if we compute the gradient of the log of like this form, then what we can see is that actually this becomes equivalent with basically having the original score here and plus some kind of the additional term, which is basically defined as kind of the gradient of the expected the virtual reward, the reward of computed with the expected output. Makes sense? Then what actually we can see is that in the continuous deformulation, that becomes the same thing like with this. So last time actually we have seen that the inverse problem can be seen as by defining the reward function as kind of the minus of the L2 loss, right? So if you plug that, the minus of the L2 loss, then actually you can see that this becomes exactly the same formulation with the DPS formulation that we have seen. So this is basically kind of the another way to basically having some interpreting the formulation of the DPS, not based on the DDPM formulation, based on but basically some more like RL style kind of deformulations. Makes sense? So yeah, I skipped some of like the details here, but here the basic idea is that we explicitly basically introduce this kind of the trade-off between the like reward maximization and also the deviation from the original the data distribution. So based on those kind of the trade-off, we basically introduced a new data distribution here, P0 dista. And then the problem becomes like, how we can sample from that, right? And based on the formulation for the new the data distribution, what we just need to do is that we just need to derive the distribution for the intermediate data point of the xt here. And then also approximate the optimal value function in this way. I mean, there can be multiple other ways. Even you can consider training another neural net to learn this. Actually, there is some kind of some approach for that, which is basically not stable, see some kind of reasons. But so this is kind of like some simple way to approximate the optimal deep value function. And based on this approximation, the good thing is that now we can simply compute the score in this way. And we can say that this becomes basically the equivalent in terms of basically having the original score plus some kind of some additional score, which is now computed as the gradient of the expected the future reward. And that becomes basically identical with the formulation that we have seen in the DPS case. So I'm just like introducing this in terms of that there are also kind of the multiple ways to basically interpret the same thing from the different perspectives. So you can see that this is another kind of the way to derive the DPS formulation this way. Any questions on this? So if I show some kind of the more applications like based on this, do you have any kind of the ideas in terms like what you can do with this kind of the idea using for your the team project or for any other things, given any kind of some pre-trained the model that can generate some kind of some realistic data points? What kind of some sort of the guidance we can try to add to make something new? So basically, the examples that also I've shown last time were all about basically for the image generation, the image generated models, right? And also how about how we can make some kind of some specific the types of the images based on the pre-trained image generated models. But actually also something that I'm going to introduce today and also the Wednesday as well are also about how we can make something the new in terms of that that's not something that can be directly generated from the pre-trained model. So for example, like given some kind of the pre-trained like image, the diffusion model, how can it generate something more than images? So those are also some kind of the interesting questions. So one kind of the example for that is basically also that some applications here is that we can also do some kind of make some kind of the more than the images using the pre-trained image, the generated models, something like this 3D or some kind of some panoramic images. So for example, like one thing that I'd like to show is that if you see some kind of the many pre-trained image diffusion models, including the model that you are also using for your the team project, you'll see that those models are basically generating some kind of the images in the certain resolution, like 512 by the 512 or some kind of into the certain resolution. So here the question is that what if we want to make some kind of the images in the much bigger size or some kind of the random ratio, or some kind of some more like panoramic images, or some 360 images, or the many other things. For that, like obviously the kind of the best idea might be is that we are just training another the diffusion model for that. But one kind of the idea in terms of like making some random size kind of the images using the pre-trained model is that we are performing the diffusion process simultaneously from the different kind of the perspectives. So this is kind of like one example that we're having some kind of the big canvas for the image, for the panorama image degeneration. And we are basically dividing this big space into the smaller space, where basically we can directly generate images using the pre-trained model. So let's say this is the size that has been used to train the pre-trained the diffusion model. And we want to generate some kind of the much bigger image like this. And what we do is that we are basically making some kind of the bunch of the windows like this box with some kind of the loss of the overlaps here. Then the question becomes like we are performing the generation the process on this kind of the multiple those kind of the some small squares while making the these overlap regions to share exactly the same thing. Make sense? So every time when you perform the generation the process through the inside these like the multiple the boxes, we perform the yours process like in parallel while just like ensuring that the overlap region here basically shares exactly the same thing. Can you define the reward function for this?
Overlap has to be.
Yes, I mean, we can come up with some kind of reward function for that, right? I mean, we can compute the 2Ds for the both of the parts and making the 2Ds, the overlap region here becomes the same, right? We can just define some kind of L2 loss, where we can use some kind of the predefined some kind of style loss even to match the style across the all the kind of the windows here. So this is kind of some simple the idea, right? I mean, we can apply those things into make some kind of some good panorama images like this. So these are all kind of the examples like making some panorama images based on this idea without having any kind of the new diffusion model or the flow models for that. And the same thing also can be applied to the make some kind of a 360 images as well. Obviously, there will be some kind of lots of some kind of the implementation the details in terms of how to achieve some kind of best quality. I'm just like giving you some kind of some ideas in how we can apply the same idea to make some many other things. And also the same idea can be applied not to make some kind of some 2D things, but also the 3D things as well. So if you are not familiar with some kind of some graphics, kind of a vision, kind of the literature, but even without that, basically the thing is that here we want to add some kind of some color information defined on the over the surface here, while we only have the image diffusion model. For those kind of cases, what we can do is that we are basically, what we want to generate is some kind of the color information over the surface here. But the thing is that we only have some kind of we only have the diffusion model that can produce some kind of some projected images here. Now we can apply the same idea in terms of that when we basically sort of do the reverse of the projection, projecting 2D things over the 3D surface from the multiple views. We want to make the overlap over the 3D regions to be exactly the same. So we can basically apply the same idea in terms like making some 3D textures as well. So we can also make those kind of things into adding some kind of colors over the surface by having those kind of some synchronization the idea. So basically, I recommend you to try to consider those kind of some kind of reward function that can make some kind of the many new things, giving you some kind of the ideas of like what you can do with the pre-trained models. So actually, for those kind of desynchronization, the easiest way to perform this is basically exactly the same thing with the kind of the DPS kind of things. But we can do even like the easier way in terms of that. We first basically sample all the XT here in some kind of the space that we call as the instance space, and then project all the things into the canonical space. This is the real space that we are generating kind of the data points. And here, we just make the toides to be basically exactly the same in the overlap region. Basically modifying the toides, and then based on that, we also update the kind of the xt-1 for all the instant spaces. So we can apply the same idea. And actually, this simple the idea has lots of the applications, some interesting applications. Have you heard about the ambiguous images? Some kind of the cute examples. Here, this is now oil painting of the people here. And if you flip, it becomes the oil painting of the old man. And here, the painting of the house plants. And after some flipping, it becomes the painting of the Einstein. So it's basically about making some kind of the images that can have some two or multiple different kind of the meanings, depending on some kind of a transformation that you're applying to the image. Some interesting examples. Right? For those kind of the cases, can you see how you can define the canonical space and the instance spaces? Yeah, those kind of the outputs can be generated using exactly the same idea, depending on how we define the canonical space and the instance spaces, and also some kind of some averaging the function. Another similar example, infinite zooming in of the images. Yeah, So let me play this again. Starting from the image of the galaxy and getting into the planet here and all the way to the some details into the some what's that? Some kind of the some buildings there. Interesting. So this is actually kind of the video, right? But this is also created using the pre-trained image diffusion model. And can you see basically how you can basically generate those kind of things? So it's basically having some kind of the more details into the singularity region, right? So it's also a matter of like how we define some kind of this instance these spaces for each of the level, and also doing some kind of the some synchronization. Some other examples here. Obviously, for those kind of things, there are some kind of more some details in the implementation in terms of to achieve some kind of the best quality. But I'm just giving you some kind of examples like what you can do with this kind of the some test time kind of scaling things. And also for the motion generation, what we can also do is that for some kind of the pre-trained model, they can make some kind of the shoot the time, the sequence of the motions. We can make it the longer in terms of basically somehow combining the multiple the shoot motions into the long motions while making the transition to be smooth using this kind of some synchronization technique. So those are some kind of also all the applications in terms like what we can do with some kind of the graded ascent from the future world. So compared to the previous technique, as I also mentioned last time, the good thing for this is that this is really some kind of the general technique that has some lots of some broad applications. For whatever the case is, like when you define some kind of the differentiable the Liouville function, you can try to apply this technique. While there might be some kind of some details in terms of how we can achieve some kind of best quality. One kind of the downside for this is that actually the real kind of the downside is that there can be some failure cases. That's kind of the one thing. And also the other kind of the big downside is that the Liouville function should be differentiable because we are performing the gradient descent and gradient ascent in this case, right? So one more kind of things that I'm going to briefly mention today is that how we can also apply the kind of the same idea for the cases that we are not having the differentiable Liouville function, but also for the non-differentiable Liouville function. And this is kind of the most general kind of technique. So if I go briefly with those kind of things, that if we go back to the idea of the test time scaling for the LLM, so this was basically the case that we are having the proposer and the verifier. So if we really think about some kind of pre-trained the LLMs, pre-trained the proposer and some kind of the existing the verifier, what would be kind of the best way to, some simplest way to basically achieve some kind of the better the outputs by spending more compute at the test time? The easiest idea that you can come up with. Any thoughts for that? You might hear about this, but this is even the easiest kind of the way. If you have any kind of the proposer and the verifier, and if you have unlimited amount of the GPU, the resources, then what are you going to do to improve the quality of the outputs? You haven't thought about the case that you have unlimited GPU resources. When you have some proposer and the verifier and you have the unlimited amount of the GPUs, then the easiest way is that you just like generate lots of things and just choose the best one. No? That's kind of the easiest way. So you just like run the proposer multiple times with some kind of some randomness there, making some kind of the multiple stochastic randomly outputs or realistic outputs, checking all of them with your the verifier and picking the best one. That's kind of the best thing, right? Actually, this is really something that the GPT is doing. The Gemini is many kind of LLM are already doing this kind of thing. This is kind of the easiest way, right? But what also people are briefly here, they discussing what now is being discussed for now is that how can you also make this kind of the process to be more efficient? Because you still need to basically run this kind of degeneration process until the end. Especially for the LLM, it also takes lots of time because it's like really sampling the token sequentially in an iterative manner. So after basically generating all the tokens, we will be able to compute the reward, right? But what people are basically talking, especially the LLM side, is that there might be some cases that we can introduce the process reward. The meaning of the process reward is that in the intermediate, the process of the generation, can we still basically define some kind of the reward for the intermediate outputs? For example, like for some kind of the math problems, when the LLM is producing some kind of some math formulations, we can still check whether the formulation is correct or not for the intermediate outputs, right? And also for some code, you can still check whether the code will basically make some kind of the compile error or not with some kind of intermediate outputs as well. So for those kind of cases, when you have some kind of the process reward, we can consider leveraging this in a way to basically making the generation, the process to be more efficient, which basically means that we are basically making multiple trajectory of the generation here, and based on basically what the signal that we are getting from the process reward, we can cut each of the branch, right? If we see that already this kind of the generation, the trajectory is kind of bad in terms of our process reward, then we don't need to generate more, right? So we cut those kind of branches and then branching out some kind of some more promising branches like this. So we can consider those kind of some more like making those kind of some tree structure in terms of making the generation, the process. Make sense? I mean, simple some engineering the idea. Then the thing is that obviously we can consider doing the same thing for the diffusion and the flow models. Diffusion, the generation, the process is also iterative process. So we can also do the same thing, basically branching out into the multiple trajectory and the cutting kind of things based on like what we have with the process reward, and continue for the more promising the directions. The same idea also can be applied to the diffusion and the flow models. But what would be some kind of the major difference between the LLM and also the diffusion of the models? So LLM, the iterative process of the LLM is basically making every single token, like some kind of the word in the text, right? The diffusion is basically the denoising the process, right? Having the intermediate XT. And what's the difference between these two? Zero idea. So basically for the diffusion model, the intermediate data points is really partial the output. We only have the partial information. We just have some kind of in the middle like generation some kind of the full sentence. And based on those kind of some literally some kind of the partial output, we need to be able to define some kind of the real function. So there are very specific cases that we can define some kind of the process reward. For many of the other cases, it's even not kind of clear how we can really define the process reward before we are seeing some kind of the full outputs. But one small kind of difference between the LLM and the diffusion and the flow model is that for the diffusion and the flow models, the intermediate outputs are kind of the partial in terms of that is kind of some sort of the blurry and the noisy outputs, but still it's having the entire content, right? And even we can easily compute the expected final output with one step from any intermediate kind of the outputs, right? So which means that the way like we are defining the process reward can be different. In the LLM, the process reward should be something that we can really define with some kind of some partial observation. But for the diffusion and the flow model, the way that we are defining the process reward can be actually things. I mean, we can actually consider any reward function that we are computing for the final output can serve as some kind of the process reward, because we can already use some kind of the Tweedie's formula to compute the expected final outputs. So there's kind of some small difference in terms of basically how we can define the process reward, both for the LLM and also the image and the video generation. In terms of in this case, we don't need to define any kind of some special process reward. Any of the reward function that we have defined for the final outputs actually can be directly employed as our process reward, which sounds like that. No, this is kind of the much kind of the easier setup in terms of applying the test time descaling in a like much more efficient way. Make sense? Clear? So this is kind of the high level the idea. I'm gonna so there are some kind of few more things in terms of how we can basically apply those things. But so let me get back to this next Wednesday. Before we wrap up for today, if I briefly introduce what we can do with those kind of things, is that so based on what we can do with those kind of some particle filtering, the idea is that now we can use any of the non-differentiable reward function as well. So for example, if you ask whatever the image degenerate model to do like produce image with the object here with exactly the certain amount, you're gonna see that there are many kind of the hallucination, not really matching the number of the objects you need to see. So we can basically make the number of the objects to match exactly the same some kind of the amount that we are specifying. And also for the text alignment, now we see that the text alignment can be easily done with the classified free guidance, right? But still, there are many kind of the cases that the text alignment is not very accurate with the pre-trained models. So we can further improve this kind of the alignment to the text with any kind of some the vision language model, so with some kind of the verifier the model. So this also can be done. And also many other things. Even for the cases that when you can have some kind of the differentiable the reward function, we can also apply the idea of the particle filtering in a way that we can further improve this kind of the quality. So if I show some kind of the interesting examples like here. Obviously, there will be some kind of the no realistic images having like 4 drums and the 7 tomatoes and the 5 candles, right? So this is really unusual kind of images. For those kind of cases, actually, we can make some quite realistic images like this with some exact match of the number of the objects here. So let me show some more extreme cases. Can you check like whether this image really have some like 82 blueberries and also 33 coins? For those kind of some very extreme cases that we want to exactly match this kind of number of the objects, we can use those kind of the test time descaling the idea. And also we can do many other things. For example, for actually the many cases, even when you try something like this using the GPT-4o or the 5 or something, then you can see actually there are some kind of the failure cases not exactly matching the given the text. So this is not the meaning of like unoccupied chair, right? But we are basically having those kind of chair without the back part, and we can precisely match this kind of some text description using the test time scaling the idea. So those are some kind of the applications for the Inference-Time descaling. So next Wednesday, I'm going to briefly wrap up those things. And also we also briefly discussed the idea in terms of how we can make something new, some new kind of the modality of data using some kind of pre-trained models, like making some 3D or the panoramic images with the image diffusion models, right? So I'm gonna get into some more the techniques for that, and I'm going to wrap up the course. Okay, let's end here.